Good afternoon, everyone. I welcome everyone to Faculty Development Program, that is Data Analytics and Business Research. Today we have session on time series analysis, which will be taken care by Dr. T. Mallikarjunappa sir. So as you all know about today's resource person, because he already engaged a session on Saturday on descriptive and inferential statistics. So directly, without wasting much time, I will welcome Mallikarjunappa sir for today's session. And the platform is yours, sir. Thank you, sir.
Yes, good morning to you all. Sangmesh, if you have any problem with my voice, you will have to tell me. Clear, right? Voice is audible? Sangmesh? Hello?
Sir, you can start this session, sir.
No, is my voice audible or not?
Sir, you can start this session, sir.
No. Sangmesh, is my voice audible?
Yes, sir, it is audible, sir.
Audible, yeah, that is what I wanted to know, because when I'm speaking, you should also be able to hear me.
Yes, sir, it is audible.
Audible, correct. Okay. And the slide movements also, if there is any problem, you'll have to tell me.
Yes, sir, sure, sir, sure.
If there is nothing from your side, I assume that the slides are moving properly, and then you are able to hear my voice also properly.
Correct, sir. Both
Correct?
are right. Yes.
Yes. All right. Now, time series analysis in business research, that is going to be the topic of today's discussion. About 1 hour, 20 minutes I'll talk, and then leave about 10 minutes, last 10 minutes for discussion from your side. Hopefully somebody will come out with something that either you can add or criticize, whatever from your side you want to do, you are most welcome to do that. Now, let me get back to what Professor Sharma was talking the other day. I entered Professor Sharma's session just to know what are the things that Professor Sharma would be discussing in regression analysis, so that it would also help me to pitch my talk on time series today. And I would request, if there are any statisticians or anybody who is read in this area, to add to what I am going to discuss, maybe at the end, or if you want to interrupt me in the middle and then want to add something, you are most welcome to do that. Now, Professor Sharma was discussing about the regression and then correlation. He was also giving the example of Sir Francis Galton, who was not a statistician, but then was trying to find out what is the average height of the sons of the tall fathers and then the short fathers. He also gave the example of how this regression, that is regressing, going back. So that's what the regression analysis, and then we have this correlation. We would be using some of those things, some of those results, but then for my purpose, because when we are talking about this in commerce and then management, I would perhaps be navigating from the generalized mathematical or statistical model to some of these, commerce and then management applications. All of us as commerce and management teachers are familiar with the regression equation. Let's say y cap is equal to alpha I, or in simple language, yi is equal to a plus bx plus e, error. So we normally write this in terms of y cap to denote that these are estimated values of y as opposed to the actual values of y. Y cap I is equal to, if a is replaced by, you can still keep the English alphabet a, but most often in the security analysis language and also in derivatives language, these are replaced by the Greek alphabets, and therefore I'll be using some of the Greek alphabets to demonstrate how the time series analysis would be useful. So if A in the regression equation y is equal to a plus bx plus e is replaced by A is intercept, A is replaced by alpha, and to say that alpha could be different for different series, alpha I plus bx. What is b? B is regression coefficient, x is an independent variable. So I will replace b by, again, a Greek alphabet, equivalent Greek alphabet beta I, and then xi to denote that xi is a variable, plus English alphabet E is again replaced by another alphabet in Greece, that is epsilon. These are the standard notations that are used in most of the time series analysis. Therefore, just to put this, y cap is equal to alpha I plus beta I into xi plus epsilon I. And again, in the securities analysis language, if you refer to any of the books on portfolio management or security analysis, this yi again is replaced. What is y? Y is a very generalized alphabet that is used, and therefore in the security analysis language, when we are talking about different asset classes, we use again an English alphabet, but not y, but y is replaced by r. What is this r? R is the return series. So ri cap, to denote that these are the estimated values of the returns. Ri cap is equal to alpha I plus beta I, and xi as an independent variable is replaced by rmi. You can still keep xi, there is no problem, but to be more specific in the security analysis box, they have used the word, the English alphabet, R, again the subscript M to denote that it is market, R is the return, M is the market, and if you are talking about different, again, the market indices are market, it could be RMI plus epsilon I. This is what we are going to use in what we normally term in statistical language as OLS. What is this OLS? Ordinary least square regression. Now, when we use ordinary least square regression and then test whether or not the regression coefficient is significant, alpha is significant, suppose you give the x series and then y series. In an equation, y is equal to a plus bx plus e. If you feed the data of x series in Excel and then y series in Excel and use the function, let's say regression in the Excel has a function for regression, and ask for the output, Excel gives output. What is the output that you normally get in the Excel? You will get what is called as the multiple R, then simple R square. Then you also get some F statistic, significance of F. Then you will get alpha, beta, that is A intercept, and then regression coefficient. Corresponding to that, value of the coefficient is given, standard error of the coefficient is given, and again, the t values corresponding to these are also given, followed by what we call as the probability values. And Excel also has the versatility to give 95% confidence intervals for both alpha and then beta, or the intercept and also regression coefficient. Now, when we talk about this, whether the regression coefficient is significant or not, normally what we look for is you have two different ways of assessing whether the t value, say regression coefficient is significant and then the intercept is significant. We can have two different values. One is the t value itself. You have the t values, computed values of t. That is what you are going to get from the Excel output. If you use SPSS, again, you are going to get the same output. You can also use eViews, Stata. You have different softwares that are available today. You know, R software is available, and then Python is available. Varieties of softwares are available today. You can use any of those things, but normally if you have the Office, you know, you get the Excel, and Excel has these functions, and normally if somebody wants to fit the regression, Excel has more versatility. Therefore, if you don't want to use many functions. Excel normally I prefer to use. You can use some other software, but I prefer to use Excel. Now, when we are using these things, let's say Excel output or SPSS output or eViews output or Stata output or R output or even Python output, any of these things, they give varieties of these estimations. When they give these varieties of estimations, now how do we know that these estimations are right estimations or not? Now, one of the assumptions of regression analysis, when we are using regression, that is, when we are regressing X on Y, or the other way, we basically assume that the series X and series Y have same mean and variance throughout the series. In other words, in the technical language, we assume that there is homoscedasticity. If this condition is violated, that is, if the series that we have at our disposal, the data that we have at our disposal, violates the basic condition of the mean being constant and variance being constant throughout our analysis. That is
sorry to interrupt.
Yeah.
Sorry to interrupt.
Yeah.
Are you changing the slides or yet you are on the first
No,
slide?
I have not yet changed.
Okay, sure. Yes.
I have not yet changed the slides. I'll tell you when I change the slides. I'll tell you.
Okay, sure, sir. Thank you. Thank
you. You should get an idea of what these things are before because people will get scared if I show equations. Therefore, I want them to become familiar with the general interpretation of this before we get into the equations.
Sure, sir.
Right? Okay. Yes. Now, when we are using these, the basic assumption is X and Y variables have constant mean and variance. But when we take the asset prices over a period of time, maybe the GDP of a country over a period of time, exchange rates over a period of time, and varieties of these variables which are observed with reference to time, we have seen, and it has been demonstrated by the researchers, that the values keep increasing in certain cases, values keep decreasing in certain cases. If you take the profit of Infosys has been growing after they founded this enterprise. If you see the profits of certain enterprises like the Reliance Petroleum, Reliance Power, the profits have been declining over a period of time. So when you see an increasing numbers over a period of time or decreasing numbers over a period of time, you find that the mean and then the variance of these types of series may not be constant, may not be same throughout the time series. If this is the condition of the data and you go ahead and use X variable as an independent variable, Y as a dependent variable, and use your regression, it violates the basic condition of homoscedasticity. Therefore, normally what is advocated is, if the data under consideration does not exhibit the constant mean and constant variance, we have to check whether the assumptions are met. At the glance, just from your eyes, if you are very clear that it is not constant over a period of time, that is mean. I'm not saying that data should be constant, but mean and then the variance are not constant over a period of time, and you observe it, then normally we say, okay, ordinary least square regression may not be a very suitable one. If you continue to use, we get the erroneous results. And therefore, what is advocated is we navigate from the OLS models, ordinary least square models, to the models that capture the basic characteristics of the time series. And that's precisely what we are going to see today. What are these models which try to capture the characteristics of the data which has time varying mean and variance? It could be only one, that is time varying mean and variance may be constant, or time varying variance mean may be constant, or both. In any of these situations, the regression violates the basic conditions, and therefore we navigate from the OLS ordinarily square method to the time series models. So we are going to see the different time series analysis techniques that are available when the data under consideration is not homoscedastic, but it exhibits the characteristics of what we call in the technical language as heteroscedasticity. If the data exhibits the characteristics of heteroscedasticity, then the ordinary square is not preferred. Now, this is a basic introduction that I wanted to give. From now onwards, I'll be changing the slides. When I change, I'll be saying I'm using the next slide, and therefore, if it is not visible, you have to tell me I'm going to the next slide now. I hope the change is visible from
Yes,
your side.
Yes, sir. Sure.
Yeah, this is precisely the outline of the entire presentation, classical linear regression, that is CLRM. Then best linear unbiased estimator, steps involved in ordinarily square. I'll not get into details of all these things. Assumptions on unobservable errors. That is, the error terms are not correlated. We will see all these things. Then time series components. What are the different components of time series? Perhaps in the statistics books that you are using to teach at the graduate level and also postgraduate level, different components of time series are visible there, but we have used some of the models there. Maybe I'll also refer to them, and then we will see what are the limitations of these. Then we see the time series modeling, then the properties of time series. Then we have what is called as the stationary process. Then time series model using different models. If you are not familiar, don't be frightened with these terms. If somebody has not been exposed to these things, I'm just giving you some glimpses, and maybe from now onwards you can pick up, and then if you are convinced that, okay, there are other models which we can use when the basic conditions are violated, then I think the purpose is served. We have what is called as the ER models, MA models. We're going to see what are these ER models, MA models, ARMA models, ARIMA models, and then volatility modeling models, ARCH models, and then GARCH models. We are going to see these things. Now, this is our classical OLS. This is precisely what I was trying to see. When I move the cursor, is the movement of cursor visible? Sangesh or anyone who is? Just tell me whether the movement of cursor is visible.
Yeah, everything.
Now, just take a look at this. We have, in fact, I should be writing here y cap, but I have just, because I didn't want to complicate too many. If there are people who are not very familiar, they might get frightened, and therefore I have not put all those things in highly technical language. OLS yi is equal to, this is yi, that is the dependent variable, alpha I, then beta I, xi, ui. You can use epsilon or ui or any of these terms. These are only estimators. This is alpha 1. If you are using series number 1, you can call it as alpha 1, alpha, say beta 1. So you have alpha 1, estimator of that is given by this equation. Beta 1, estimator of that. This is cap, means it is an estimated value and not a true value or actual value. Now, alpha 1 and beta 1 cap estimation of all these things are the estimators of true values of alpha 1 and then beta 1. Please understand this true value of alpha 1 and beta 1 we do not know. Therefore, what we try to do is we take certain data that is available with us and use that data to check whether these can be estimated. Now, the true values are represented by their estimates. The best way is to put the true values. That is, what is this intercept, what is this regression coefficient itself. If you know actual value, true value of the entire population, that is the best way. You can put beta 1 value and then alpha 1 value. But unfortunately, we would not be knowing that. And therefore, we use the sample data to estimate. That is why this cap denotes that it is an estimator. Now, these are linear estimators. Linear estimators because we are using the linear expression. That means the formula for alpha and beta are linear combinations of the random variables x and then y. I hope those who are teaching some of these things you are familiar. If for a regression equation of y is equal to a plus bx, the simple terms that are given in the statistics books that we normally use in commerce and management, you have sigma y is equal to a sigma x plus another one b sigma x, and then sigma xy is equal to a sigma x square plus b sigma a sigma x plus b sigma x square. That is, these are the two simultaneous equations that we normally use for estimating a and b. The same equations are used here, but how do you get these two simultaneous equations? These two simultaneous equations we derive from what we call as calculus, that is differential calculus. And what is this concept of calculus that is used there? In differential calculus, we take the first derivative and then the second derivative, equate it to 0, and then solve for these, and that is how we are going to get these two simultaneous equations. You may have heard of the term called the maxima and then the minimum. So we use this concept of maxima and then minima and try to estimate this alpha, say A and B, and the same A and B are denoted as alpha and then beta. So A estimation is alpha estimation, B estimation is beta estimation. They are called as linear combination because we are putting B1, X1, or Xi and then alpha. On average, the actual values of alpha 1 and beta 1 will be equal to their true values. This is estimated values are expected to be equal. Now that means that the OLS estimators have the minimum variance among the class of linear unbiased estimators. So this is based on the Gauss-Markov theorem. Now the steps involved quickly in this economic or financial theory, we have the previous studies. If somebody has already done that, then, and if they are given the estimators, and if you believe that that estimator is the correct estimator, you don't find any problem with that, perhaps you can go ahead and then use. But if you feel that, no, I don't want to take this because there are some limitations of this, then you formulate a model that you want to use for estimation. Then based on that model, find out what are the variables that are required for this and collect the data required for this. Then estimate, that is the model. You have the model that you have already a priori set, and then you have the data that you have collected from that model. Then estimate this. Is the model statistically adequate? If the answer is no, reformulate this model. If the answer is yes, then interpret the model, then use it for analysis. Again, same thing, general statement of the problem. Some of these entire thing I'm not going to read because of the paucity of time. You have the data collection, choice of the estimation, statistical, including softwares that you are going to use. So I have already told you what are the different softwares that are available. So what are these? Quickly, just to recapitulate, what are these some of the terms, because these are the terms that we are going to use in our time series analysis. Assumptions on unobservable errors. Now, what are these errors? Unobservable errors. Errors are simply when we are trying to estimate the true values from the sample values. Again, we are using intercept estimator as the true population intercept, and then again beta estimated using the sample as the true beta values of the entire population. And I'm sure all of you would agree that whenever we are using the sample and trying to estimate the population characteristics based on the sample characteristics, there is every possibility that we go wrong. And therefore, what are these deviations? The actual values, how far the actual values deviate from the estimated values. So actual minus the estimated value, we call them as errors. How far these errors? Larger the errors, less is the precision of our estimation. I'm sure you would understand this. Then the variance of the errors is constant and finite over a period of time. And these error terms, suppose I take the sum of all these error terms, that is, I have y1 as one estimation, y2, y3, y4, y6, etc., all those things. And then I have the true values of y1 true value, and then estimated value, true value minus estimated value, next true value of y minus estimated value. I take all these things and I designate them as u, that is the error terms, u, t over a period of over different observations. This is expected value of ut, that is the mean value, is expected to be 0. That is the sum of the error terms in any of the models that we are familiar. Model is OLS, it is expected to be 0. And then variance is this, variance of ut is sigma square. This is our standard deviation that you are going to, which you are taught. If you take the square of standard deviation, that's your variance. Okay, then we have this concept of covariance, because this is covariance term is extremely important in all time series. What is this covariance? Perhaps all of you know what is covariance, but you may not have used it widely, but you have used what is called as the correlation coefficient. Correl-Pearson's coefficient of correlation. Professor Sharma was making a mention of Correl-Pearson's coefficient of correlation. Now, Correl-Pearson's coefficient of correlation varies between +1 and -1. That is less than or equal to +1, but greater than or equal to -1. This is a relative measure of the relationship between two variables under consideration. A corresponding absolute measure to measure the relationship is covariance. How do one variable vary with the other variable? Say, let's take this as X series, this as Y series. So Ui and then Uj. How do they co-vary? So if you do not take the standard deviations to the denominator of your correlation formula, sigma small xi yi divided by n becomes your covariance. Similar to that, we also calculate what is the covariance of these things. Now, covariance ui, uj, that is maybe covariance between the first term and then the second term, first term and the third term, fourth term and the fourth term, all these things. It is expected that the covariance will be almost equal to 0. When I say 0, in actual practice, it may not be exactly 0. So in the technical language, they are called as errors are not correlated. Linearly independent of one another means there is no error of this. And then again, covariance between ut, that is the error term, and xt, that is the independent variable. It is also expected to be 0. And then ut, that is the error terms, follow this term is used. Ut follows normal distribution with mean 0 and the variance sigma square. This is your standard normal distribution. Standard normal distribution, it has this formula Z is equal to xi minus mu divided by standard deviation. That is exactly the standard normal distribution, which is independent of the unit of measurement. This is precisely what we are referring to here. The error terms UTs are expected to follow standard normal distribution. N stands for the standard normal distribution with mean 0 and variance sigma square. That is, UT error terms are normally distributed. Now, assumptions of unobservable errors. What are these unobservable errors? These UTs are unobservable errors. Now, assumptions of unobservable errors in the OLS model, when we are using the OLS model, one is stationary series. The series of these errors are stationary. We will see what is the stationarity in the subsequent slides. Errors are free from autocorrelation or serial correlation. What is the meaning of autocorrelation and serial correlation? First error is not correlated with the second error. First error is not correlated with the third error. First error is not correlated with the fourth error. Or the series of errors, when we take them as X and Y with different lags, they are not correlated. So there is no presence of autocorrelation or serial correlation. And then again, this is the term which I have used. The series are homoscedastic, and there is no absence of series are homoscedastic means there is absence of heteroscedasticity. Errors are normally distributed. This is precisely what I was trying to say. Stationary time series. Just take a look at this. This is the graph which shows how the entire thing, there is an upward movement, and again there is a downward movement, upward movement, downward movement. You can just see upward movement and downward movement. Whenever there are movements, they again come back to the mean. Upward movement, it has come back to the mean. Downward movement, it has come back to the mean. Upward again, come back to the mean. Downward movement, come back to the mean. So if you see this as the mean value, there is an upward and downward movement, and this looks stationary. You will just see uncorrelated errors. And then again this. And what is this normal distribution? This is your normal distribution. The middle is the mean ordinate, and the mean ordinate has mean as 0. I'm talking about standard normal distribution. If you are taking the original scale of X, please understand, original scale of X would not be 0. But if you standardize that, the mean ordinate and then the standard deviation would be sigmas, and variance would be sigma square. Mean would be this. This is 0. You have 0.5 standard deviation to the right, and then 1 standard deviation, 2 standard deviation, 3 standard deviations to the right. And if you want to extend infinitely, you have plus infinity. This side, again 0.5 standard deviation. This side 0.5, 1 standard deviation, 2 standard deviation, 3 standard deviation, and minus infinity to the other side. This is your standard normal distribution. Now this is homoscedastic. This is the heteroscedasticity. Now let's come back to this time series and see what is this time series. A time series is a set of observations taken at specified time intervals, normally equal intervals. Suppose you are taking daily share prices of, let's say, Reliance Industries Limited. Daily share prices over 10-year period. That is a time series because I'm taking day 1 of, let's say, 2000 and day 2 whenever they are quoted, and observe these share prices of Reliance Industries with reference to the time period. That's a time series. I collect the GDP of the country every quarter. That's a time series. I collect the exchange rates of INR versus British pounds, INR versus Japanese yen, INR versus Australian dollars, INR versus Singapore dollars, INR versus Hong Kong dollars, INR versus Canadian dollars, US dollars, etc. over a period of time. That is, every day I collect this. This is a time series. The data have been collected over a period of time on one or more variables. I can collect different data. I can collect the data of GDP, then along with that GDP, I can take that per capita income, I can take disposable personal incomes, and I can take varieties of these things. I can take more than one variable. The simplest example that I can give is, suppose you have collected the data of the, let's say, exports and then imports of this country before the liberalization and then after the liberalization period from 1992 onwards and before 1992. Over a period of time, every year you have collected the exports and then imports. This data is your time series. The frequency is simply the measure of interval over period of time. That is either daily or weekly or fortnightly or monthly or quarterly or yearly or decades. What is the data that is collected once in a decade? Census of India data is collected once in a decade. So the data are collected and then recorded. Series examples they are given here, which I already said. IIP, Index of Industrial Production, is being compiled to find out how the industrial activity is going on in the country. So industrial production, it could be collected on monthly basis or quarterly basis. Government of India budget deficit on an annual basis, when the finance minister of the country presents the budget to the parliament, which used to be on the last day of February, which has now been advanced to the first day of February. Then money supply, maybe M1, M2, M3, broad money, narrow money, supply all these things either on daily basis or on weekly basis. That becomes again a time series. Then again the price of any of the shares that you might be interested in working on. That's your time series. Now, importance of time series data. We use the time series data. I'm sure you would understand that people want to find out what would be the GDP of this country, how the GDP of this country is going to grow in the years to come. Next year, IMF has given an estimation, World Bank has given estimation, different independent think tanks have given estimation, Ministry of Finance has given estimation, and then Niti Aayog has given its own estimation. So this is business forecasting. Then understand the past behavior. If you have to forecast into the future, I have to understand how this behaves in the past so that I would be able to find out what is likely to be its behavior in the future. The current hot topic of discussion for forecasting is, will there not be any third wave of the pandemic, world war? These are being predicted. And to model these things, will there be second wave, will there be third wave? People are looking at, okay, when Spanish flu came, was there only one wave or was there a recurrence of the second wave? The answer was, they looked into the past data and found that there was a second wave, and there are predictions that there will be second wave. Now there is prediction that second wave is almost coming to an end, but in certain states it has not come to an end, but there is a prediction that there could be a third wave. That's forecasting for the future. Then if you want to plan for the future, then also the time series is required. Then evaluate the current accomplishment. So what are the different components of time series? Time series has these components: long-term moments and then short-term moments. Within the long-term moments, long-term moment could be upward and then downward. There may be trend. It could be simply horizontal to the x-axis. It could be a stationary trend, non-stationary trend. Then short-term movements, there could be seasonal variation, like your summer, winter, and then different seasons. There could be seasonal variations. There could also be cyclical variations. Now, for this cyclical variations, you have seen things like your boom, recession, depression, then recovery. Like example is your business cycles. So within each cycle, if you take the short-term moments, they could be termed as cyclical moments. Then you have the random or irregular moments. These are different components of the time series. This is an example. This is a graph to show how the time series when it is plotted with x-axis as the time and then y-axis on the y-axis. Although I have not written the y-axis, you have to assume that there is a y-axis. That is the case with even the normal distribution. We had not put the y-axis, but y-axis is always there. Y-axis measures the probability there. So similarly here on the x-axis, we have the time period. On the y-axis, we have the values of any variable that you are trying to observe. Let's say this is the depiction of the GDP of the country, or this is the depiction of the varieties of whatever variable that you are observing. So you put the values on the y-axis and then time period on the x-axis. The time period that I have put on the x-axis is a dry number 1, 2, 3, 4, 5. You can perhaps put it after liberalization 92, 93, 94, 95 up to 2021 you can put. Or if you want to put before liberalization, I want to observe from 1980, 1980, 81, 82 up to let's say 1991. That is before liberalization. And then after 92, after liberalization, put it on that graph that is here, and then here put it on the graph and see how the entire graph looks like. So if the graph looks like, this is the demonstration of what are these irregular fluctuations. I hope you are able to see that. Then you have the cycles. Please understand, this is the cyclical movements. You can just see here the cyclical movements. Then if you observe a period, over a period of time, there is some type of an increasing trend. There is some type of a trend. You can just see here. Then you have some seasonality within these things. So you can observe these are the components, the graphical representation of this. Again, the trend, suppose you have, this is a bar chart, and if I connect all these bar charts, there is a downward movement of all these things. Financial year 1992, 93, etc. up to 2020, 21, and then something I am observing, maybe I am observing profits of the company. Any variable that you want to represent, you put it on the y-axis. This is a declining trend. It would be a profit of the company. And then there is the same thing, an upward trend. I gave the example, if you take Reliance Power, the profits are declining, sales are declining over a period of time. If you take Reliance Industries Limited, RIL, both sales and profits are increasing over a period of time. So that's declining trend, and then inclining is a increasing trend. There is a seasonal pattern. Short-term movements is affected by seasonal factors such as time of the year or day of the week. Seasonality is always fixed and with known frequency. You can just take the same thing. You have an independent variable and then the values of the variable that I'm going to observe, that is the dependent variable on the y-axis, and then independent variable or time period on the x-axis. In most of the time series analysis, when I draw this x-axis, that x-axis denotes the time period. Now the short-term time movements, again, take a look at this. Then output, maybe GDP of the country, just take a look at this. There's an expansion, and then there is a boom, and therefore there is a peak, and then it comes down, recession, and then you have this point, depression, then there is a growth. So this time series, over a period of time, this is happening, and these are the characteristics of the time series. This is precisely what we are trying to demonstrate. Random or irregular movements are those which cannot be predicted. Statistical noise or error terms. In time series parlance, when this component is completely random, not autocorrelated, it is termed as white noise. Okay, time series modeling. One attempts to model using the time series data. Now using own past values and information. We try to do this, and let's see how to do this using own past values or information. along with using other explanatory variables. I can use the past values of the same variable, and along with that, I can also combine other explanatory variable, which I think is likely to influence the dependent variable. That's again a different type of model using the current and then the past values of an error term. UT, we just saw in the OLS regression, we have this UT and error term, and we generate these error terms, and error terms themselves are used for modeling the time series data. Now, different properties of time series. If anybody wants to ask anything, you are most welcome to interrupt me. I would welcome in case you have this. If you do not have any doubts, I assume that you are listening and then you are understanding. If some of you are not able to follow, perhaps you would be able to follow once again when you listen to this. We have these properties of time series. One is the stochastic process, stationary process, white noise process, autocorrelation, random walk phenomenon, and then we see all these things. Then we will just see what is this stationarity, which is very, very important in the time series analysis. A random or stochastic process is a collection of random variables ordered over a period of time. Ordered in time means observed over a period of time. If we let y, that is any alphabet. Normally y is used, but you can use any alphabet, not necessarily y, but this is the standard notation that is used. Denote a random variable, and if it is continuous, that is, you have the discrete and then the continuous. If y is continuous, we denote it as y in brackets t, but if it is discrete, we denote it as y suffix t. But in a standard language, we don't really make much. When we are writing, we don't really make these differences. We just use this yt to denote these variables. It can be denoted as y1, y2, y3, y4. If it is y1, that is year 1 observation, we call it as y1. So t assumes the value 1. If it is year 2, t assumes the value 2. If it is year 3, t assumes the value 3. So it y1, y2, y3, yn could be, say, GDP of India starting from 1992 GDP. I can call this as y1, 92 GDP, y2, and then 93 GDP, I can call it as y3, and then 2021 GDP, 2020 GDP as yn. Keep in mind that each of these y's is a random variable whose values you can't predict. Now let's quickly take a look at what is this stationary process. Stochastic process is said to be stationary. I have made a mention of this. If its mean and variance are constant over time, and the value of the covariance, that is the value of the variance between two observations taken at two different intervals of time, that is today and then yesterday, today and day before yesterday, today and 3 days back, today and 4 days back. That's the meaning. Different intervals of time between the two time periods depends only on the distance. I'll explain what is this. Only on the distance or gap or lag between the time periods and not the actual time at which the covariance is computed. Now what it says is, suppose I am observing the GDP of this country and I am taking the covariance, maybe of the error terms or any of these things. I am putting GDP of 1992 and then I try to find out whether the 1992 has relationship with 93, 94, 95, 96, etc. all these things. And then in another case, let's say I am taking 2000 with 2001, 2002, 2003, 2004. Now what it says is, it depends on the length of the time period or the time lag, not on the actual time period. It means it does not depend on whether you have taken the 90 series or 2000 series. I took 1992 as the starting period, correlated with 93, 94, 95, 96, etc. And then another series, I took 2000, 2001, 2, 3, 4, etc. I correlated with that. So it does not depend on whether you have taken 90 series or 2000 series or 2010 series. So suppose I compute the correlation coefficient between this and this, it only depends on the time lag, whether you have taken lag of 1 or lag of 2 or lag of 3, and not whether you have taken 2000 or 2010 or 1992. That is the meaning of this. In the time series literature, such a stochastic process is known as weakly stationary. Please understand the spelling W-E-A-K. The person is very weak. That is the word that is used here. Weakly stationary or covariance stationary or second order stationary. Now that's the mean of this is expectation. E stands for expectation. This is the probability language. Expectation, which is actually the mean value. Expectation of yt is mu. This is again a Greek alphabet. Population parameters are normally denoted by the Greek alphabets. Sample characteristics are normally denoted by the English alphabets. So the variance of this yt is given by this yt minus mu. That is in our BCom, BBM, MCom, MBA language, we normally call it as yi minus y bar. So that y bar is replaced by mu, that is the population mean. So expectation of yt minus mu square, because we are talking about variance, is equal to sigma square. Now sigma has two cases, like the English alphabet. You have small letter and capital letter. Greek also has this. This is small case. We call it as lower case. And then the uppercase is also pronounced as sigma, but that sigma is for summation. Lowercase sigma is for the variance, sigma square. Now the covariance. Covariance is denoted by this, that is, you have yt minus mu, yt plus k, that is, we add some lag to this, the further number, minus mu. So suppose this is y1, and this is, let's say, k is equal to 1. This becomes y2. That is expectation of yt, that is y1 minus mu, and then y2 minus mu. That is your covariance. So over a period of time, we observe this is the interpretation for all these things. What is this number and all this? So this is the stationary process. In short, if a time series is stationary, its mean, variance, and covariance or autocovariance are constant or invariant at any lags. Mean reverting. In the graph, I showed you how they were fluctuating, but they were coming back to mean. That is the process of mean reverting. And fluctuations around this mean measured by variance will be constant. So non-stationary series are weak stationary, or time varying mean, and then variance, or both. If it is non-stationary, mean may be varying over a period of time, or variance may be varying over a period of time, or both may be varying over a period of time. Now, what is the problem with this non-stationarity, and why do we require stationary time series? Non-stationary time series provides only for time period under consideration. One of the problems with non-stationary, each set of time series data will therefore be for a particular episode. It is not possible to generalize to other time periods. Such time series are unsuitable for forecasting. Model with non-stationary time series results in spurious regression with vast estimations. Now, to summarize all these things, if the characteristics of the time series are varying over a period of time, the problem of using those types of time series is our prediction is simply not possible. If you go ahead and predict, then those predictions would not be the right predictions. So if you want to use the time series data and learn how the past has behaved and want to use that past behavior to predict into the future, you are assuming that past holds good into the future. But unfortunately, that is not true if a series is non-stationary. That is precisely why forecasting becomes erroneous forecast if you are using non-stationary time series data. Therefore, you have to ensure, if you want to model them for forecasting, you have to ensure that the series is stationary and not non-stationary. Let me quickly go through some of these terms. I don't think I'll have so much of time to explain all these things. Stochastic process, purely random, zero mean, and constant variance. I have just now told you what is this. UTs are IID, normally distributed with zero mean and then variance, standard deviation. What is this IID? Independently identically distributed as standard normal distribution with mean, zero, and constant variance called sigma square. Now the random walk model. I don't know whether any of you in the audience are teaching security analysis and portfolio management. If you are teaching security analysis and portfolio management or even investment management, we have what is called as the efficient market hypothesis there. In the efficient market hypothesis, we talk about three different forms of market efficiency. One is market is efficient in the weak form, market is efficient in the semi-strong form, market is efficient in the strong form. Of course, there are also higher level efficiencies, which is not the topic of this discussion. But what I'm trying to drive home here is this random walk model is widely used in the security analysis and then investment management to test whether or not the market is efficient in its weak form. So random walk model, RWM, stands for the random walk. It is often said that the asset prices, such as the stock prices or exchange rates, follow a random walk. That is, they are non-stationary. What are the types of random walk? Random walk without drift, no constant or intercept term. I have the equations for all these things. I'll quickly show you these things. Then random walk with drift, a constant term is present. Just to drive home this random walk, what could be the best example for random walk? Quite often, the example cited for random walk is the path taken by a drunken man. If a person is completely drunk, and if you want him to find out a way to certain places, you will know that he will not move straight into that house. He will go drift towards maybe the canal, drift towards a person who is doing something there, drift towards a child when he says. So he takes different directions. And very often, if you want to see what is the direction which he has taken and whether he has reached the destination after half an hour or 1 hour, the best place to find out whether this person, where is this person, is the place from which he started. Perhaps he may not have moved, but he may have taken many steps. So this is quite often cited as one of the examples for the random walk. Now this is the random walk. model without drift. I'm coming to equations because in the time series, this is an inevitable part. Equations are inevitable part of the time series. So if some of you are averse to this, you have to bear with me. But if you want to work on some of these statistical models, you have to be very familiar with these. So we have this random walk. Yt is equal to, yt minus 1, that is yt. Let us say yt stands for today's price. What is t minus 1? 1 day before. If I am measuring daily, today's price is determined by yesterday's price, yt minus 1 plus ut, another term. Just to give you most familiar example, normally what we do is, suppose we want to predict the GDP of the country for the next year, we look at what was the GDP of the country last year, what was the GDP of the country 2 years back, 3 years back, 4 years back. And if you feel last year's GDP will influence this year's GDP, and then 2 years back GDP will influence this year's GDP, 3 years back GDP will influence this year's GDP. The best way to model that is last year, that is yesterday, and then that today is influenced by yesterday, plus this error term. It is called as AR1. What is this AR? AR stands for auto regression. What is this auto regression? I am trying to regress one period previous to this on to today's. So yt minus 1 on this. Why is it called without a drift? There is no constant term here. So this is a specific case. Instead of t, subscripts are used here. Suppose I want to do it for day 1. It becomes y1. What was the previous number? y0 plus u1. ut, please understand, u1. I want to do it for day 2. It depends on day 1 plus u2. And it can be written as, in place of y1, I am putting this value. Please understand this value. There is y1. In place of y1, I am putting this value. That is y0 plus u1. Then you have this u2. Suppose you want to do it for day 3, or year 3, or week 3, or month 3, or fortnight 3, or third quarter, any of these things. Y3 is equal to Y2. It depends on the previous quarter or previous day, and then the error term U3. Then for what is the definition of Y2? Y2 is this. The entire thing is substituted here. So Y2 is again this particular term. So what I'm trying to do here is I'm trying to substitute Y2 is this, then this, and then this term is taken as it is. So since you have U1, U2, U3, and since the numbers are changing serially, I can sum up all these error terms using this uppercase Greek alphabet called as sigma, and then I use the same alphabet. U, then T, where T varies from maybe 1 to M. I can put it as 1 to M or 1 to M, whatever, Y0. Yt is equal to Y0 plus sigma ut. So this particular term, some of you are able to follow, I would be happy. Now I get back to this. Suppose in this, I take this yt to the other side. So what I have done is, I have taken this yt as it is. Then yt minus 1 from this side, I have taken it to this side. And this yt minus t minus 1, I have called it as delta yt. Delta again is a Greek alphabet. And this delta operator is used for difference. Difference between t and t minus 1, yt minus 1, delta yt is equal to ut. The same thing, it is done here, first difference. Variance of yt is given by t into sigma square. So these are all the properties. I'll go to the next one now. A random walk with drift. So in the random walk without drift, please understand there was no constant term. Random walk with the drift, there is a constant term. This is also delta, that was also delta. This is lowercase delta, that was uppercase delta. Delta plus yt minus 1 plus ut. That is, this is a constant term. This is again an independent variable, that is the previous observation. This is another term. And this is a drift parameter. That is intercept, it's a drift parameter. If I take yt to the other side, yt minus 1, that becomes delta yt is equal to this and then this, that is delta and then ut. That is, yt shows drift upwards or downwards depending upon the value of this delta. Then random walk with drift, expectation of y1 is equal to y0, that is y0 plus t into delta. Variance of this is, these are the properties, you don't need to bother too much about this. Then random walk model with drift, the mean and then the variance increases over a period of time. You would understand this by nature. If you have this over a period of time, if it increases like this, mean and variance increases. Volatility, the conditions of stationary, violating the conditions of stationarity. If the mean and variances are increasing, it violates the conditions of stationarity. Random walk model with or without drift is a non-stationary stochastic process. This is without drift, this is with the drift. Now take a look at this. There is no constant. This one, there is a constant term. This is with drift, this is without drift. Sanmesh, how much time do I have?
So 20 more minutes.
Sanmesh?
20 more minutes, sir.
Another 20 minutes. Okay?
Yes, sir.
Yes. Just relax for 1 or 2 minutes. Because
yes,
some of you feeling it's an overdose.
Yeah. Meanwhile, if anyone has any queries, you can put in the
1 or
chat
2
box.
minutes only, you just relax. Good afternoon. I'll call you. I'm in a session. I'll call you maybe after. Huh? Yes. Okay. Okay, let's quickly go through some of these. You have yt is equal to, now there is another term which is coming here. This is again a Greek alphabet, rho. You have the English alphabet R to denote the correlation coefficient. Normally English alphabet R is used for denoting the correlation coefficient of the sample. This rho, that is the Greek alphabet, is used for denoting the correlation coefficient of the population. So rho varies between -1 and +1, less than or equal to +1 and but greater than or equal to -1. If rho is equal to 1, is random walk model without drift, then this is known as unit root problem, a non-stationary situation, a random walk. So if rho is less than 1, In time series, YT is stationary. You can take a look at these graphs. Let me quickly go to the next one. This is GDP. This is personal disposable income, personal consumption expenditure, varieties of these things, profits of the company over a period of time, dividends of the company over a period of time. This is the graph would also give you some type of an idea whether the mean is varying or remaining constant. So this is, suppose you have this, you have a trend. Is the trend determinable? Can I find out with certainty? Then that is a deterministic trend. If I am not able to determine exactly, because it varies and then lots of variation which I'm not able to predict, then it's a stochastic trend. A trend in a time series is completely predictable and not variable, is a deterministic trend. A trend in a time series, if it is not predictable, it's a stochastic trend. So let me not get into the equations of these, because I think we have another maybe 15 minutes, at least 5 minutes I have to have for the discussion. So you have some of these properties, deterministic versus, stochastic time series models. So I have some more. Now what do we do if the series is not stationary? Random walk without drift is non-stationary, but its first difference is stationary. First difference is, I was just telling you, yt minus 1. I was showing that, delta yt. That's the first difference. So random walk without drift is integrated of order 1. When I say order 1, integrated of order 1, it means I have taken difference once. That is the first difference. It is denoted as I, English alphabet I, in brackets 1. 1 to denote that I have taken difference once, and I to denote that it is integrated of order 1. So in general, we normally say YT, differenced time series, is denoted as D. Therefore, I, then D. How many times you have difference? D times I have difference. So YT is integrated of order D. So if YT is integrated at order 0, that means the original time series itself is stationary, and it is absolutely fine for you to use maybe the techniques like your regression. We call it as level stationary. If it is integrated of order 0, that is, I have not taken any difference. I have taken the original series, and that itself shows the characteristics of stationarity, and that is integrated of order 0. But if you have to make that series differenced, maybe once or twice or thrice, so it is integrated of order D. D could be 0, then level stationary, D could be 1, then it is stationary, it has become stationary at first difference, D could be 2, it has become stationary at difference T, say 2. Employment of non-stationary time series in the model results in spurious with biased estimators. So, yeah, I think I have told some of these things, integrated of order 1, 2, 3, all these things. So I will perhaps skip these things. These are the technicalities, integrated of order 0 and then order 1, and then these are the properties. What happens if you have xt as one series, yt as another series, and both of them are integrated? I will skip because there are some more time series models. I'll quickly go through some of these time series models. So if the data that we have is exhibiting time series characteristics, we apply different models for analyzing the time series data. What are these different models? Number 1 is simple autoregressive models, ER models. Then simple moving average models, MA models. Then mixed autoregressive, and then moving average, called as ARMA models. ER and MA, if you combine, it becomes ARMA models. Then you have the seasonal models. Then you have the regression models with time series errors. And then fractionally difference models for long range dependence. So we'll quickly go through these things. Time series models, assumption. One of the things that we assume is when we are using, we have to make it stationary. Errors are free from autocorrelation or serial correlation. If that is violated, you have to make it. Then homoscedasticity or absence of stationarity. Errors are normally distributed. This is, I have already shown these things. And then what are the stationarity tests quickly? Whether the data is stationary or not, how do we make out? One is take a look at the graph. You can put it as a line graph and then see whether there is a trend in that. If there is a trend in that, and if the mean and variances are increasing, then that's an indication that there is heteroscedasticity in the data. Then autocorrelation, that is, take the correlation between the past value, today's value, and yesterday, today's, and 2 days back, today's, and 3 days back, and all these things, and find out whether there is an autocorrelation. If there is a presence of autocorrelation, again, the series is non-stationary. Then another one is the unit root test, whether or not the unit root exists. That is, rho is equal to 1. That's what transform the series. If you find that the series is not stationary, then transform. One of the transformations, simplest transformation is you can take the difference, first difference, yt minus 1, that is delta yt, that itself is one of the transformations of the data. Graphical, how do you graph this data? This is an example of graphic. Autocorrelation, this is your correlation, simple correlation formula. But here the difference is I am taking the correlation between today's value minus the previous, say, today's and then yesterday's and then day for yesterday's and all these things. Series is same, but we are taking the past values. That's, then we have the partial autocorrelation. Then parallelogram is one of the methods of this. Then this is again unit root test, very famous unit root test is called as ADF, augmented decayfuller test. So delta yt is equal to, you can put this and then find out presence of the unit root. And another method used is Philipperon test. In fact, in practice, what really happens is you are not going to compute all these things. The statistical package that you are going to use will give you what is the DCF value, PP values, whether the unit root exists, but you should only know how to interpret these numbers. Unfortunately, these numbers are not available in the Excel. If you want to model that using Excel, then you have to put the formula for the decayfuller test and then perhaps run that formula. Excel works, but there is no ready-made decayfuller test in Excel, Philipperon test in Excel. So that's, then the difference stationary, that is the example, GDP of today minus GDP of the previous days or previous quarters, whatever it is. You can take these things, okay. So this is, let me just see whether we have, yes, autoregressive models. Just take a look at this. I'll only show that these are the different models that are available without getting into the details of this. YT, that is the dependent variable, is based on YT minus 1, that is 1 day before. YT minus 2, 2 days before. YT minus P, P days before, plus the epsilon t, that is the error term. So if it is modeled as independent variables or the past value of the variable itself, it is an autoregressive ERP process. Now, another way of modeling, in the previous case, we took the previous values. In this case, what we are taking is, we are modeling them as the error. Hello? Call me after 50. I'm in a session. After 15 minutes, you just call me. I'm in a session. After 15 minutes. Okay. So suppose I take the independent variables as the error term, that is epsilon t, then epsilon t minus 1, t minus 2, all these things, then this becomes a moving average. The difference is, in the AR model, previous values of the variable is taken. In the MA model, the error terms, including the previous values of the error terms, are taken. Then ARMA, please understand, in the ARMA, what we are trying to do is, we are combining ER, in the ER, what did we do? Past values of the variable. And in the MA, values of the error terms. So we have the error terms values here, then the past values of the variable itself, xt. Instead of yt, I am using xt. That's all. That's all here. So this is the past values of the variable, past values of the error terms, MA model. So that's. Then we have ARIMA, that is autoregressive integrated moving average model. Here we have the previous values of the variables, error terms of these variables, and there is an error term present here, which was not there in the earlier cases. So we call it as ARIMA, that is autoregressive of pth order, integrated at dth order, and MA at qth order. So ARIMA PDQ. All these values the software will give you, but you should know what is this P, what is this D, what is this Q. So this D is how many differencing error terms you have taken, what is the lag that you have taken for the error terms. P is what is the lag that you have taken for the variable itself. And D, how many differences you have taken for making it stationary. ARIMA, P, D, Q. These P values, D values, Q values, all these numbers, it is possible for us to find out using different criteria. So it has white noise and then random walk with drift, autoregressive, and then we have this moving average. So I'll quickly glance through this. We have what is called as the BJ methodology, identification of the models, parameter estimation, and diagnostic checking. And then we can use it for forecasting. What are the identification? These are the details of this identification. Then if we find that the stationarity is the series is stochastic, and then it exhibits heteroskedasticity, that is volatility clustering, then we have some of these problems. And volatility clustering example is this. Then the models used for these, we have the conditional mean and then the variance. Conditional variance of the error term, arch or volatility term. This is your mean equation. This is your variance equation, arch. So we have this particular model. ARCH stands for autoregressive conditional heteroskedasticity of order Q. So that's, then we have Garch model, generalized autoregressive conditional heteroskedasticity. So this is again a mean equation. This is a variance equation. If you want to use it, do it by manual calculation. It takes quite a lot of time, and therefore the softwares today have all these things incorporated into this. Last one is the references that we have used for this preparation of the slides. Damodar Gujarati, which is one of the most important and very widely used book. Earlier it was only single author, Damodar Gujarati, but now we have three authors, Manshikar, Porter, and then Damodar Gujarati. then Chris B, introduction to econometrics for finance. And let me also thank all of you for this wonderful opportunity. And now the floor is open for discussion. I would also like to take this opportunity to express my gratitude to my own student who helped me in preparing these slides. She is Rajini, who is working in the Government College, Kalayamidi. No, Kapu. Government College, she is an assistant professor. She did PhD with me, and she helped me in the preparation of all these slides. These are the references. Forum is open for discussion now.
Thank you, sir. Audience, if you have any doubts, you can ask the question in comment box. Sir, we'll wait for 1 or 2 minutes for this.
Yeah, fine. Okay. Stop screen I will put, okay?
Yes, sir. Yes, sir.
Or do you think there will be any questions? I'll still put the screen on if there are any questions, if they want to show any of the models. Okay, stop screen. So I stop sharing.
Yes, sir. I think there is no doubt from any audience, sir. So I think everything is clear from all the participants, and it was really a very technical session. We got to know a lot of things. Yes, sir. Thank you very much for being part of this faculty development program. In your busy schedule, you accepted our offer, and you were ready for the engaging 2 sessions. So we really very thankful to you, sir. Thank you very much, sir.
Thank you, and I am happy if it was useful for all of you. I know
Yes,
time
sir.
series is slightly technical unless somebody is exposed to this. The very notations, Greek notations are scary. Therefore, I didn't want to scare all of you. That is why in the beginning, without moving the slides, I gave introduction. But of course,
sir.
there is one issue. We have to introduce the equations and then these Greek alphabets if you have to make familiar these time series models. So fortunately, what is happening today is you have a lot of softwares that have incorporated all these things. You have ready-made softwares. Like I was telling you P, I was telling you D, I was telling you Q, all these numbers you can find and get it from the software. But if you know how the model looks like, you would be able to interpret what is this. Otherwise, for you, it becomes a Greek and Latin. Yeah. So fine, thank you all. Sangesh, shall we start?
We are running on some technical issues, sir. So that was a very great session.
Yeah, fine.
Yeah. We will be, sir. Are you willing to share the presentation with the participants? Like we will be doing it from our side.
Yeah, I'll do that. Maybe I'll
Yeah.
make slight modifications because
Okay,
some of
sure.
it are taken as it is.
Yeah.
There can, because if it becomes a public document, I have to
Yes.
acknowledge. So
Sure, sir.
yeah,
Sure.
I'll
So I
make
hope it is clear to all the participants. So now we are moving to the concluding part. So the feedback link for the session will be shared on your emails and as well as in the WhatsApp group participants. So kindly be attentive and do fill the feedback without missing it.
You have valedictory tomorrow, or you have
Yes.
today?
Tomorrow, sir.
Tomorrow. Yeah. Okay then. So
Tomorrow there
bye.
is a
Thank
last
you.
session, sir.
Thank you. Thank you. Yes. Who is
Yes, sir.
handling tomorrow's?
Sir, tomorrow it should be supposed to be handled by Krishna Kumar sir from Osmania University,
Okay.
but due to his self health health issues,
Ah,
he is not engaging tomorrow's session. So I think Hugar sir will engage tomorrow's session, sir. So still it
okay.
is pending, sir.
Okay.
Like
Okay.
we also consulted different resource persons. By the
Okay.
evening, you will get to know like who is the resource person for tomorrow's session, sir. I think
Okay.
it's probably Hugar sir will engage tomorrow's session, sir.
Just send me the link. If I am free, I'll join.
Sure, sir.
But
Sure,
I
sir.
have another session. Just send me. If I'm free, I'll join. Otherwise, I wish you all the best. Thank you very much.
Yes, thank you, sir. Thank you, sir.
Bye. Okay. Yes. Yes.
Yes, thank you, sir. Thanks a lot, sir. Thanks a lot.
Thank you. Yes. How did you feel? Was
Thank
the
you, everyone.
discussion
Good day.
useful?
We'll be ending the session now.
Was it useful, Sanmesh?
Thank you, everyone. Thank you.